All right, so in this lesson, we're going to continue on with our thermochemistry. This time, we're going to be talking about enthalpy and endothermic and exothermic reactions. And endothermic and exothermic reactions are something y'all have talked about over the years in your different science classes. And hopefully, you remember that endothermic reactions are the ones that are absorbing energies from the surrounding. And that means the container would get colder. And then exothermic are the ones that release energy to the surroundings. So then if we had a reaction going on, the container would feel hotter. And last time when we talked about heat, we talked about it in terms of absorbing or releasing energy, what their signs would be. And so, of course, absorbing energy is endothermic, so the sign for that, of course, is positive. And then if it was an exothermic reaction, it is releasing heat, so that heat value would be a negative sign. This picture is a picture of the Hindenburg accident that happened a very long time ago, as you can tell by the black and white picture. And obviously, it was an explosion, so obviously that was indeed a very exothermic reaction. So let's talk about the system versus surroundings, heat going in, heat going out. First of all, we need to define what the system is, and that is what is actually being changed or studied. Example, the reaction itself, whether it's getting hotter or colder. And then the surroundings is everything else that's not involved directly into the reaction. Okay, in the case of an endothermic reaction, heat is going into the system and it's coming from the surroundings. And it's the opposite for an exothermic reaction. It's leaving the system and being released into the surroundings. So this is an energy diagram of an endothermic reactions. As you can see, we have energy on the y-axis, and down here we have time on the x-axis. So as time goes on, the energy of the system obviously changes. This is endothermic, and we always know it, we can recognize an endothermic by the fact that the products have more energy than the reactants. And the reason that the products have more energy is because they absorbed energy in the reaction, and so therefore when it's completed, the products would have more energy than the reactants. And of course, as you would expect for an exothermic reaction, the energy diagram looks the opposite. In this case, the reactants will have more energy than the products, and that's because, in this case, the energy was released from the system in an exothermic reaction, and so therefore the products would have less energy because it released some of the energy. If you did not take the time to label your energy diagram in your notes, then you should do so at this time. So this brings us to enthalpy, which is used to quantify the heat flow into or out of a system in a process that occurs at constant pressure. And so here again, we have energy differences between exothermic and endothermic. And this first one is an exothermic reaction. And so heat would be given off by the system to the surroundings. And so in this case, remember we said a while ago, energy was going to be less for the products than it is for the reactants. And so your delta H value is going to be less than 0 or negative. And then, of course, over here in endothermic, now we have heat being absorbed. So remember, our products had more energy than the reactants. And so that delta H is going to be greater than 0 or it will be positive. So this is just summarizing the previous slide. So I want to make sure you understand, and you're just going to have to memorize this, that delta H is positive for an endothermic reaction, and then delta H is negative for an exothermic reaction. And the one that's actually favored is the exothermic. It is the favored reaction because nature likes things towards a lower energy, and so it will be favored in most cases. So here's a little bit better definition of enthalpy. It is the amount of energy absorbed or lost by a system during a process at constant pressure. And we've got a couple of different types of enthalpy. The good news is they're all calculated relatively the same. We have heat of formation, which is when we're forming a compound from its constituent elements. We have the heat of reaction, heat of combustion when we're burning, heat of vaporization, and heat of fusion. The good news is they're all calculated the same. It's just what's going on. We call them different things. So how we're going to be seeing this stuff is called a thermochemical equation. And it is a balanced chemical equation, just like we've been doing, that includes the physical states of the reactants and the products, and it also includes the energy changes. And it's going to be expressed as either a product or a reactant. when it's expressed like this, it is actually the delta H value, but we're putting it in the equation. And then, of course, I want you to make note of this in your notes. If you need to pause it to write this down, go ahead and do that. If it is an exothermic reaction, delta H is still negative, but we write it as if it's a product, like we have here. So this one we have shown here is actually an exothermic reaction. And that's because since heat is being released, it appears as a product. If it is an endothermic reaction, the delta H value is still positive, but it's actually going to appear as one of the reactants because we are having to add that energy into the system to get the equation to happen, or to get the reaction to happen, rather. And so it will appear as one of the reactants. That gets a little bit confusing for kids, and so you need to make note of that you understand that. If it is a product, then if we were to write the delta H value by itself, we would write it as negative. But if that energy appears as a reactant, then when we write that delta H value by itself, we would write it as a positive number. All right, so let's do a stoichiometry exercise, and I hear the collective groan of you saying, oh no, not more stoichiometry, but it never really goes away now that we've learned it, so let's just continue forth here. Here we have potassium hydroxide in a solid form being dissolved in water, and it says that it goes from solid to aqueous, and then it's plus 43 kilojoules. And so it wants us to answer the following questions. So number one, it wants to know, does the beaker get warmer or colder? Okay, and number two says, is the reaction endothermic or exothermic? And then number three says, what is the enthalpy change for the dissolution, which means dissolving, of the 14 grams of KOH? So we're actually going to answer the first two together because you kind of can't answer them separately. It wants to know if the beaker gets warmer or colder. Well, we kind of need to really determine whether this is an exothermic or endothermic reaction first before we can answer that. And so, of course, we just said in the previous slide that whenever the energy appears as a product, that it is an exothermic reaction. And so, of course, this is an exothermic reaction. And so because it's an exothermic reaction, when we dissolve those potassium hydroxide pellets, the beaker will actually get warmer. Okay? So we've answered those two, but now it wants to know what is the actual enthalpy change if we only dissolved 14 grams, okay? So what we have to remember at this number right here is the same as our delta H. So our delta H is actually, it is 43 kilojoules, but because we know it's exothermic, it's a negative 43 kilojoules, okay? But that is kilojoules per 1 mole, okay? When we write it like this, it's always going to be per 1 mole of reaction. And so because of that, we actually need to figure out how many moles of the KOH we have because we have 14 grams. And so I'm going to work that on the next slide. All right, so I just rewrote that. We had the KOH solid going to the KOH aqueous plus 43 kilojoules. And so we said that means that's a negative 43 kilojoules per mole, and we were given 14 grams. So since we were given 14 grams, we're going to start with the 14 grams, and of course, 14 grams of KOH. And so we are going to need to convert that to moles of KOH, and we do that using the molar mass, just like we've been doing for quite a while now. So the molar mass of KOH is 56.11 grams per 1 mole. And if we go and look at the reaction that we have up here, we see that for every 1 mole of KOH, there's 1 mole, and remember in the reaction, because we said right here that this was kilojoules per 1 mole. And so now we've got grams to cancel, and we've got moles of KOH. So now we can use that for every 1 mole of reaction, and that RxN is just an abbreviation for reaction, there is negative 43 kilojoules. And so now it's just a matter of doing the math, and I believe when that comes out, I have that written down somewhere, we do the math, we multiply the top, divide by the bottom, and it comes out to a negative 10.73, and then we need 3 significant figures because it gave us 14.0 kilojoules, but we also have the 43 here, and so we actually need 2 significant figures, and so we're going to say that this would be a negative 11 kilojoules would be our answer. Okay? That is where we're going to stop today. The rest of this lesson for enthalpy is going to be done in class because it's a little bit trickier, and so we'll do that in class. Stay tuned for the jokes on the next slide, and of course, if you don't want to listen to them, then stop the video here. So, in honor of Easter, I thought I would do some Easter jokes. So here we go. Where does the Easter Bunny get his eggs? From an eggplant. What happened to the Easter Bunny that misbehaved at school? He was expelled. And what day does an Easter egg hate the most? Well, Fridays, of course. And lastly, where does the Easter Bunny eat breakfast? At IHOP. All right, I hope you have a hoppy Easter.